In this video, what I'm going to do is I'm going to go over an example of how to calculate the magnetic potential. So this is example 511 from Griffith's books on electrodynamics. And what you have is a spherical shell of a surface charge of sigma. The shell has a radius capital R, and it's rotating with an angular velocity omega. So that's what's going to give us the magnetic phenomenon, is that once we start rotating this charged sphere, then the moving charge is going to create magnetic fields. And from that, we can actually figure out what the magnetic potential should be. So if we were to draw a picture of it, so here's my sphere. It's got a radius, capital R, and I want to figure out what the magnetic potential is at some point out here, R, and it's rotating with an angular velocity omega around this axis. So the angle between the axis of rotation and the point at which we're trying to measure A, that angle is called psi. Okay, so now we want to put this on a coordinate system. And so we have a few choices of how we want to orient it. We could put the axis of rotation on the z-axis, but instead, I think what we're going to do is we're going to put the shell at the origin. The center of the shell is at the origin. We're going to put the point in space that we want to measure the magnetic potential on the z-axis. So that means the distance from the origin to our point is r. The distance from the origin to a point on the sphere where the charge is, we're going to call that r prime. And the distance between those two is script r. Now, so this vector r prime is at an angle theta prime with respect to the z-axis. Its projection is at an angle of phi prime in the xy plane. And the last thing we need is the axis of rotation, which I'll put here, and as I already said, is at an angle of psi with respect to, in this case, the z-axis. Okay, so now that we've got the coordinate system drawn out, now we can write out all the pieces to our Coulomb's law. So to calculate the magnetic potential with Coulomb's law, the equation is mu0 over 4 pi integrated over the charge density, in this case the surface charge density, which is at some position r prime, divided by the distance r, and integrated over the area. Okay, so let's put the base of three pieces. Let's write them down with common variables. So the current density is the charge density times the velocity, how fast it's moving. The area is r squared, because we're dealing with a surface area, times sine theta prime, d theta prime, d phi prime. So we basically integrate over the entire surface area. And lastly, for script r, that's just r minus r prime. We want the magnitude of it, so we can basically square it to get the amplitude, to get the magnitude, and take the square root. So using the law of cosines, though, we get capital R squared. That's what we're substituting for r prime, plus little r squared minus 2r little r cosine phi prime, and then take the square root of that whole thing. Okay. So what about that velocity? What are we gonna do about the velocity? Well, the velocity turns out is the angular velocity crossed into that distance r prime. And so if we work this out, we would have to take the cross product. So I'll use the determinant method and say I would have omega sine psi in the x direction, 0 in the y direction, and omega cosine psi. So that's the components of my angular velocity. And then for the distance, I would have capital R sine theta prime cosine phi prime r sine theta prime sine phi prime, and then r cosine theta prime for the z. Okay, so let's work that out now. So v now becomes, if I take the determinant, minus omega cosine psi r sine theta prime sine phi prime in the x direction minus omega sine psi r cosine theta prime minus omega cosine psi times r sine theta prime cosine phi prime. So all of that in the y direction, and then plus in the z direction omega sine psi r sine theta prime sine phi prime. Okay, so that's going to give us the velocity, and so now we can try and clean that up a little bit by, say, factoring out any omega r's that we have. So we would have well, let's factor out a minus omega r. And so then we would have a cosine psi sine theta prime sine phi prime in the x direction. And then I would have plus sine psi cosine theta prime minus cosine psi sine theta prime cosine phi prime. So all of that is in the y direction. Okay. And the z term is plus z sine psi sine theta prime sine phi prime close brackets. Okay, so that's that's the velocity. Now, eventually, we're going to integrate these, and so any integral 0 to 2 pi of sine psi prime d phi, sine phi prime d phi, that's going to be 0. And any integral 0 to 2 pi of the cosine of phi prime is also going to be 0. So in the end, the only term that survives is that second term, the first one in the y direction. So now we can write out this potential A as mu 0, the charge density, divided by 4 pi, integrating 0 to pi in theta prime, 0 to 2 pi in phi prime, and we would have omega times r minus sine psi cosine theta prime in the y direction divided by the square root of capital R squared plus lower r squared minus 2 capital R lower r cosine theta prime, and then integrating over r squared sine theta prime d theta prime d phi prime. Okay, so that's the integral then we have to solve. So nothing in there is phi dependent. So the integral of 0 to 2 pi d phi prime is just 2 pi. And then we can take everything out that isn't a theta. And so what we're left with is mu 0 sigma omega r sine psi 2 pi divided by 4 pi, and what we're left with then is the integral 0 to pi of cosine theta prime sine theta prime d theta prime divided by the square root of r squared plus lowercase r squared minus 2 little r big R cosine theta prime. And what I'm missing is there was a capital R squared in the Jacobian, so therefore there should be an r cubed in that constant term out front, as well as the direction, y hat. Okay, good. So we've isolated all the constant stuff. We're now left with this integral to solve. And so if we were to make a substitution, so let cosine theta prime be u, so minus sine theta prime d theta prime is equal to du. So that way I can rewrite the integral as minus 1 to 1 u du over r squared plus r squared minus 2r capital R u square root of that. So let's make another substitution, and that is we will let v equal capital R squared plus lowercase r squared minus 2r ru dv is equal to minus 2r du. That means that u is v minus r squared minus lowercase r squared over minus 2r capital R, and u du is v minus r squared minus r squared over 4 lowercase r squared capital case R squared dv. Okay, so what I'm going to do is I'm going to rewrite that integral. So the integral is now from capital R squared plus lower r squared plus 2r. The upper limit is r squared plus r squared minus 2r, and the integral is v minus r squared minus lowercase r squared over 4r squared square root of v dv. Okay, so I'll stop here, and then I will continue this in the next video.